This lecture is about universal motors. Universal motors are some of the most common and widely used motors available in industry. These are used in small portable machines because of their durability, compactness, and also their robustness. So let's look at the universal motor. So straight away you can see the construction of the universal motor. The universal motor, like all motors, has a stationary part, which is the stator, and it consists of the core and the stator windings. Okay. In addition to that, you have the rotational part, which is the rotor, and the rotor also has its own mounted windings, which are also able to carry a current. Now, in the case of the universal motor, the stator is actually the field, and we will see more about that later. And the rotor is what you call the armature. Armature is spelled like that. And it has a lot of similarities to DC motors, which we have covered in the past. And similar to other motors, you also have, of course, the bearing, which is mounted inside this casing. And you have a shaft which is connected to the load. And of course, you have terminals which you can connect a power supply. And on the right, we can see another alternative diagram, more of a diagram that shows a bit more clearly some of the components of the universal motor that were not clear before. Of particular importance to note is the brushes, which this is a difference that the universal motors have from the induction motors, which we have been covering in the rest of this unit. Induction motors do not have brushes. They transfer the power from the stator to the rotor through induction of the from the rotating magnetic field. Here, in the case of universal motors, both the rotor and the stator are electrically connected to each other and to the power supply. So the connection from the stator windings to the rotor is done through brushes and a commutator, which we have seen on this side. So in this photo, you can see the commutator, which is around here. But the brushes, you can't really see them. They are hidden kind of inside here, right? Inside the casing itself. But on the diagram, you can see them a bit more clearly. So you have brushes that transfer electrical power to the windings through carbon brushes themselves, right? And we have yet another diagram here showing these are carbon brushes. And the reason we use carbon brushes is that as the rotor rotates, the commutator and its bars or its elements are rotating, and they maintain a kind of contact with the brushes by the use of carbon. So the carbon is a self-lubricating element that will be able to glide over the commutator and maintain that physical contact through which electrical current can flow, right? And you can see a very clean exploded diagram of how the rotor fits into the air gap or the space inside the stator or the field. So this is the construction of the universal motor. So let's look at how the universal motor actually operates. So let's look at the principle of operation. So let's assume we have a current flowing into and out of the machine in the directions indicated as I have shown in the diagram. All right. We have the configuration of the windings. You can see the windings of the stator on both sides. And you have the windings mounted onto the rotor with the brushes that you have, we expect within a universal motor. And these are various windings, the windings on the left-hand side of the stator, windings on the right-hand side of the stator. And we would have, if you have current flowing into, we can expect or we can assign a direction of flow of current looking like that, as we had indicated earlier in the unit. This is a direction of current represented by the cross sections of the windings, and in this particular diagram, current is assumed to be flowing into the windings on the lower side of the stator, which means that on the upper side, they would be flowing out of the surface of the screen, right? Then you would have current flowing onward through the wire and then connecting to the rotor through the brush, right? Once it has connected to the rotor through the brush, you would then have it flowing on the windings indicated there. Let's assume this direction for purposes of our illustration here, which means that on the opposite side, they would be flowing in the opposite direction. Whereas on the right, they are flowing out of the screen. On the left, they're flowing in, okay? And finally, they flow through the other brush out of the rotor and onwards to the second half of the stator, where you have them. Let's say the current would pass behind and have a similar configuration to the left-hand side of the stator, all right, and outward to the second half of the terminal, okay? So this is your basic configuration of a universal motor that gives you a flow that, as we will shortly see, provides a magnetic field that is able to generate a torque. You can see the left-hand rule is indicated on the right-hand side, and we will show how that torque is created. So as we had seen earlier in the unit when we were talking about induction motors, anytime you have an induction motor or anytime you have a current flowing through a conductor, you use your right-hand rule through Ampere's law, indicating that the current, if you would wrap your hand around, your right hand around the current carrying conductor and point your thumb in the direction that the current carrying conductor, that the current is flowing through that conductor, the direction of the fingers, the way they wrap around the conductor, indicates the direction of the magnetic field, which we are showing here. And in the terms of a cross section, if you have current flowing into the cross section, you have a clockwise current, and if it's flowing out of the surface, you have an anti-clockwise direction of magnetic field. So applying that here, because we have several windings that have current flowing through them, both in the stator and in the rotor. If we first take the upper left-hand side of the stator flowing out of the screen, this will give us an anti-clockwise direction, which is what we have seen here. Just to recap, yeah, it's an anti-clockwise direction because it's flowing out of the screen. And similarly, on the right-hand side, you have a magnetic field that is set up because of the current, and it is also in an anti-clockwise direction. On the lower sides of the stator, on both the left-hand side and the right-hand side, you would have current flowing into, which gives you a clockwise direction. Similarly, on the right-hand side, you have a magnetic field set up around that winding, which is also flowing in a clockwise direction. So what this means is that you have generally within the core of your stator, you have a magnetic field that tends to flow all across from one side, let's say the left-hand side, to the right-hand side of the stator. And practically what we have done is we have set up a north pole on that side. Let me use a different color. We have set up a north pole on that side and a south pole on the right-hand side. Okay, north to south, and the direction of current or the direction of the magnetic field is that way. Okay, right? And so this magnetic field will pass through the rotor. Now, note that we have current carrying conductors within the rotor, okay? And they are showing in the direction, if we zoom in a bit here, the current is flowing in the direction indicated. Yeah, so you have the interaction of magnetic fields, okay, which are set up that way. So how do these now interact with the rotor windings? This is where now Lenz's law comes in, whereby Lenz's law is the left hand rule. So we now switch from the right hand to the left hand, and you have set up in this configuration of your hand. You put your hand in this position with the field of your left hand, the pointer finger, the first finger, index finger of your left hand, pointing in the direction of the field, and the current is indicated by the direction of your middle finger. So if we look at, first of all, this side, right? Let's take this particular portion of the motor, okay? You have field indicated in green pointing to the left. So you have straight away the index finger of your left hand pointing to the left, all right? Then you have your current carrying conductors with the current flowing into the screen. So that means you orient your middle finger, which is perpendicular to your index finger on your left hand side, left hand, you indicate it pointing away from you. So first finger, index finger, remains pointing to the left. You rotate your hand so that your middle finger is pointing in the direction as if it is pointing towards the screen. If the screen is between your face and, or rather your hand is between your face and the screen, the middle finger points from you towards where the screen is, and that leaves you with the thumb pointing downwards. So you find your thumb is pointing downwards. So the force or the thrust that is acting on these windings is such that it pulls them in that direction. And if we move across to the right hand side, same left hand, same index finger pointing to the right, but this time you have the current flowing outwards out of the screen. You make your middle finger point in the same direction, and that means that you will end up with a force on these windings that is acting upward, because that is the direction that your thumb is pointing. Let me use a bit better. So it points in that direction. So here we have a force on the left hand side, it is acting down. On the right hand side, it is acting up. What does that mean? It will tend to rotate your rotor in that direction. So here we have created a force such that if the rotor is free to rotate, it will be able to rotate in a counterclockwise direction. Okay. So that brings us to the second part of the cycle. So here we have indicated the opposite direction of flow of current, right? We assume that the cycle has changed. So everything in terms of the flow of current is opposite to what we had seen before. So where the current was flowing upwards, it is now flowing downwards. Where it was flowing inwards, it is now flowing outwards. So let's indicate that. And then we see how that changes the direction of the magnetic field and consequently the force or thrust that is subjected to the rotor. Okay, so you have opposite directions for everything, and let's see where the magnetic fields will flow towards. So we have magnetic fields set up as we had seen before, exactly the same. The only difference is the direction of the current, which means that you will then have in this lower side, instead of it being clockwise, it will be anti-clockwise. In the upper side, instead of it being anti-clockwise, it now becomes clockwise. And same thing on the opposite side, on the right hand side. So here we have clockwise, and on the lower side you have anti-clockwise direction. So that means, once again, another magnetic field is set up. However, in this case, the left hand side is your south pole, the right hand side is your north pole, and you have magnetic fields going in the opposite direction to what it was doing before. So what is the impact on the force in the rotor. Once again, we zoom in and we use our left hand rule. So this time, our left hand rule, the direction of a magnetic field is towards the left. So you point your index finger towards the left. And on this side, the field or the current, sorry, in the conductors is pointing out of the screen. So that means you then have the middle finger pointing between you and the screen. So it's a bit awkward if you're doing it practically, but essentially we will see that at the end of it, you still have the thumb pointing in a downward direction. And if we move to this side, orienting ourselves similarly, you would now have your thumb pointing upwards. So that means that even if you have a change of direction, the direction of the force that the rotor will be subjected to remains the same, right? Even with a change of direction of current, you have a force that remains the same all through. And that is why we call this the universal motor, because whatever direction that the current flows through, whether it is DC, whether it is AC, positive, negative, first half of the cycle, second half of the cycle, you will always have the resultant force acting on the rotor in the same direction. It is important to note once again, this type of machine is not an induction motor. It does not operate on the principles of induction simply because there's a direct connection between the rotor and the stator. The field and the armature are connected to each other electrically. Okay. So let's look a bit more into the physics of the machines themselves. Let's look at the equivalent circuit. Okay, so the equivalent circuit of the universal motor will look like this. And the components are labeled RF, XF, because this is our field winding or stator, indicated here. Okay, that represents our field winding. Here we have RA, XA, and an element EA. Yeah, this whole part of the circuit represents the armature, right? Now, the armature generates its own magnetic, or rather generates its own voltage. This is the armature, which is located inside the rotor. Okay, it generates its own voltage called the back EMF, right, which acts against the voltage supply which would be supplied from this side, right? And that back EMF means that it is the interaction of the back EMF and the supply voltage. The difference between those two is what is creating our torque here, right? The action of the voltage and its back EMF that is created within the circuit is what causes us to have our torque. And consequently, the torque, we've been looking at torque speed characteristics, and the torque and speed of our universal motor will look something like that, right? So it has a high torque at the low end, which is the starting point. So we can call that the starting. And it will gradually reduce until we have a kind of low torque at the running or rated speeds, right? These are kind of the rated speeds. So this is quite useful for devices or applications where you need a high torque at the beginning, and once the initial inertia is overcome, you can then have a lower torque which will sustain the movement of the machine. This is usually the case when you have things that you need to start on load, right? So this would be stuff like devices that are used, power tools like drills, grinders, and the like, which you would have them generally on load. Things like kitchen, portable kitchen equipment for blending and so on and so forth. They would generally use this kind of motor. So actually, these would be some of the applications. So applications include portable tools such as drills, grinders, and the like. Sometimes kitchen equipment, domestic equipment, blenders, and so on and so forth. Domestic equipment, not just kitchen equipment, such as vacuum cleaners. Generally, any small, something less than or just a few kilowatts would be a suitable candidate for use with this kind of motor. So in addition to this, some of the advantages, as we have said, it has a high starting torque. Another use is that it is portable. It gives good power for its size. And some of the disadvantages include, of course, it has brushes, and any brush, any mechanical element will generally be subject to wear and tear. So these will have to be maintained and kept in good working condition. You generally have to regularly replace carbon brushes as they do wear out. These brushes that are here, because of their lubricating nature, you can see they are mounted on springs. So as they wear out, the spring pushes the carbon brush onto the commutator, but eventually they wear out completely and they need to be replaced. So that in a nutshell is the operation and advantages and disadvantages and applications of universal motors, and we will stop there.